what is the magnetic field created at the proton because of the electron? So our proton is a charge and it's moving, so we know that a moving charge creates a magnetic field. So part D, we'll write down the Biot-Savart law that the magnetic field equals mu naught over 4 pi times Q, our charge, times the velocity V crossed with r hat. R hat is our direction from the electron to the proton, divided by r squared. So there's our proton, there's our electron moving in this direction. So let's get the direction first. With our right hand rule, we point our thumb in the direction of V, so our thumb goes this way. Then our finger goes in the direction of r hat. R is our vector from here to here, so r hat is our vector from here to here. So V goes with our thumb, R goes with our finger, and our B points out of the page. But Q is our charge, the electron is negative, so instead of being out of the page, it has to be into the page. So we know that the direction of the magnetic field at the proton is into the page. Let's find the magnitude. The magnitude of B is mu naught over 4 pi times the magnitude of the charge, which is going to be E, times the magnitude of V cross R. The magnitude of a cross product is the magnitude of V times the magnitude of r hat, but that's a unit vector, so that's 1, times the sine of the angle between V and r hat, so that's 90 degrees, divided by r squared. So we put in that E is 1.6 times 10 to the minus 19. V is our velocity we found in the previous step. R is our 53 picometers. And we get that the magnetic field is equal to 12.4 Teslas into the page. And that's at the proton. Okay, the next part, what is the magnetic moment of the atom? So we'll ask, why does it create a magnetic moment? So our proton is whipping around, our electron is whipping around in a circle, so it's a moving charge, and moving charge can be thought of as current. So the moving electron is essentially like a little current in the atom. So our magnetic moment equals I times A. Our current I is equal to the charge over the time. The time, a little bit tricky, but not too hard to find out. Let's think about what the velocity means. So it goes around in a circle, which means it travels a distance of 2 pi r over an amount of time delta t, which would be the orbital period of the electron. So that means our delta t equals 2 pi r over v. So we'll fill that in for times our area. So we have q over 2 pi r over v times our area equals q times v over 2 pi r. A means the area of the proton going around in the circle. It's a circle, so the area is pi r squared. It's pi r squared. Now let's get our direction in here. So the negative charge is whipping around in a circle this way. Remember, the definition of a current direction is opposite the electron flow. So it's like our positive charge would move around the opposite direction. So if the electron is going this way, it's opposite the direction of the electron flow, so it would be into the page. So if we went around this way, it would be out of the page, but it has to be opposite that, so it's into the page. So there's our direction. We'll cross out one of the r's, cross out the pi, so we multiply the charge, 1.6 times 10 to the minus 19, times the velocity, which we found 2.18 times 10 to the 6, times that by the radius, and we get a magnetic moment of 9.24 times 10 to the minus 24 amps times meters squared. This is really small, but then the area is really small too, so a small magnetic moment makes sense. Our last question now is, what if we put the atom in a magnetic field? What happens to it? What does it feel? So we have our proton here, we have our electron here. We're saying we're placing it in a magnetic field that points from the proton to the electron. So the magnetic field points this way, B. So we have a magnetic moment that points into the page. So that's the minus k direction if we choose x, y, and z the normal way. B is equal to the right in this picture, so plus I. So what happens is it's going to feel a magnetic torque. Torque equals mu, oh, my pen is back. Torque equals mu cross B. So it's going to feel a torque. Let's figure out the direction of that torque. So the direction of the torque is going to be minus K crossed with I. So if we like, we can remember what I cross J and I cross K and all those are. So K cross I would give us plus J, which means minus K cross I would give us minus J. Okay, and we can do that with our right-hand rule as well. So mu is into the page, B points right, so our torque direction is down. So our torque direction is down, so we think about what does that mean in terms of rotation. If torque is down, it's going to give a rotation where this spins out of the page and the other end spins into the page. So it's going to give us a rotation of the atom. So that's what happens if we put it in a magnetic field.